It's a great honor to be giving the introduction to today's talk by Professor Sipahigil, titled Optical Interconnects for Superconducting Quantum Processors. And I want to start by really showing a little bit. So today, these days, we already know that superconducting qubits already make up one of the leading platforms for quantum information processing and computing. And there are already advances that allow us to put on the order of 10 to a few hundreds of qubits under control with good fidelity. And we have also seen demonstrations of quantum advantages already in several aspects. And as these quantum information processors are becoming more advanced, we may think about connecting different quantum computers together in, for example, two separate dilution fridges to do quantum networking. Right? We might want to be able to do modular computing, or even entangle two fridges that are a certain distance apart. And the way we talk to these devices, right, is via microwave photons. So if we want to send microwave photons across fridges, then we have to make sure that the communication channel is well isolated from the environment. So here I have some pictures from, for example, Andrea's Wallraff group in Zurich, right, showing a 4K link between two dilution fridges. And if you look on the inside, right, the microwave lines, as the number of qubits is increasing, right, these microwave lines are kind of taking up spaces in a DIL fridge. But at the same time, right, usually when we are thinking about doing quantum networks, we're not imagining microwave photons. Usually we would envision optical photons, flying around networks of fiber optics. So, one approach to do this is we can think about upconverting a microwave photon into an optical photon. So we want to find a black box. We want to look for a black box that converts or transduces, say something like 5 gigahertz to something, in the telecom band, for example, 200 terahertz. And I guess one, fun fact about the telecom band, it is so low loss that, for example, the same loss, about a few dB, that you can cover with a microwave photon over a meter. You can do that with over tens of kilometers with a telecom photon. So it is very low loss. And to do this frequency up conversion, right, we want to talk nonlinearity. Right? So we wanted this black box to change the frequency. So we want to find a nonlinear system that allows us to do that. Right? So now the subject of nonlinear optics has been studied very thoroughly for decades. But these days we don't find it discussed very often in the context of quantum science. But I'm kind of hoping to convince you today that some of the kind of concepts can be kind of very useful, can give very useful perspectives when looking at phenomena in quantum optics. So when we talk about a nonlinear medium, right, what we actually mean is the polarizability response, the response to the electric field, right, goes beyond the linear order with electric field. So we can tailor expand this response in a power series, right? So, and we can name our coefficients, chi1, chi2, chi3, etc., right? Where chi1 is a linear term, chi2 is the square, goes like the square of the electric field, and so on. And you can already see from this tailor expansion that if we want to input just one field at 5 gigahertz, right, we really need to raise that to a very high power to reach 200 terahertz. So that's not going to work with one input. As a next step, let's try, introducing another input. Right, so we can think about a 3-port black box, with 2 inputs, 1 output. And here we can imagine that we might want to mix, right, kind of these this microwave signal with an optical input to get another kind of optical output, right? And these days we already have devices that work I guess under this framework of 3-wave mixing, right? 3-wave indicating the 3 ports on the indicating 3 ports from the device, right? And you can buy, for example, off-the-shelf electro-optic modulators And you can also realize this with 3-level systems, ranging from atomic vapors or rare earth ions. But how does this 3-wave mixing actually work, right? So I want to kind of attempt to describe this process a little bit more mathematically, right? So this is a Chi2 process. So if we can look at the Hamiltonian P dot E, for example. Now in the Hamiltonian, right, the lowest order nonlinear term, right, the Chi2 is going to go like E cubed. And since this is a 3-part device, right, the field inside the medium, right, it's going to be the sum of the 3. And if you expand, this E cube, you're going to find terms like, products, combinations of products, including the cross terms that, contain all of them, E1, E2, E3, with some time dependence. And, this time dependence will be rapidly varying, unless these frequencies are well matched. So for example, if we look at this term, right, it will become kind of dominant if the frequencies are matched. So here, we can imagine this dominant term indicating kind of frequency sum generation, right? So the output omega-3 is actually the sum of the 2 inputs. And kind of going back one step, right? We only want to convert, one quantum field to another. And so we can start by, we don't have to start with all of the fields quantized, right? We can, for example, leave this omega-1, the pump, be like the classical pump, and only quantize this omega-2 and omega-3. Right, so we go ahead and spell out, for example, E2 as this A2 plus A2 dagger. Right? We quantize E2 as well as E3. Right? But we're going to leave this E1 classical. And with that, we expand this one more time, do the rotating wave approximation to kind of kill the terms like A2 dagger, A3 dagger. And we're left with a Hamiltonian that looks like this. So if we stare at this for a second, right, what this is actually the same as the beam splitter Hamiltonian, right, between this A2 and A3 modes. Right? So you can think of this as, say, the definition of quantum transduction or quantum frequency conversion, if you like, right, where we annihilate, when we annihilate a photon at omega-2, right, we then create another photon at frequency omega-3. And this picture, this kind of beam splitter picture is not limited to just kind of 3 electric fields, right? But we can also kind of generalize this to any other kind of bosonic fields, like, for example, phonons, right? And we can also, quantize the phononic mode the same way we did. So here, right, we replace our E2 as, our kind of phononic operator S2. And again, we can also have a beam splitter that subtracts a phonon from the phononic mode and adds a photon in the same kind of omega-3 mode. And this is like another way of really describing what's an effect that's very well known, the acousto-optic effect. Right. So there are many AMO experimentalists here in the audience. And when we talk about acousto-optic effects, right, one thing you might think about is the acousto-optic modulator. This is an off-the-shelf device. Right? When you buy one, it comes in a box with apertures for you to kind of send a laser beam through. And here, right on the side, you also have an RF port, to kind of modulate this laser beam. So on the inside, right, this is a very kind of critical device that, I guess we cannot these days, we cannot imagine AMO physics without AOMs. But if you look on the inside, right, what it is a crystal like quartz that's attached to a piezo transducer. And the way it works is we can dump a radio frequency or microwave power onto this transducer to basically put phonons on the crystal, make it vibrate, and make it vibrate. Right. Then you send a laser beam through the crystal, and this kind of phonon via this acousto-optic effect, right? It will deflect the laser beam and transduce it to a new frequency. depending on the alignment, right, you can have, the frequency sum or the difference, or you can even have the higher harmonics of the radio frequencies. Now, the next question, we might ask is, now that we have an acousto-optic modulator, why don't we just use this to transduce our microwave photons to optical photons? And it's not a crazy question to ask until you kind of start, calculating the power. You start thinking about the power considerations. The experimentalists among you can already point out that we already know that to get substantial deflection efficiency, about 50–70%, right? We need to dump, on the order of a few watts of power onto the RF port. But superconducting qubits, right? With superconducting qubits, we work with single microwave photons, right? And if we kind of write down, calculate the power, turns out, the power per single microwave photon comes out to the order of tens of femtowatts. So this is a very, very tiny power to transduce. And but that's exactly what Alp and his team at Caltech kind of managed to achieve. So what you'll be seeing in the talk today will be about kind of how Alp and the team took the same operating principles as the acousto-optic modulator and really kind of build devices, improve to the point that we can start doing quantum transduction on single microwave photons. That said, the main basic ingredients are basically the same, right? You need the optomechanical component. In this context, this is done under the framework of cavity optomechanics. You want to make sure that you have strong coupling between different degrees of freedom. You want to make sure that the losses are low. And you have something vibrating in the cavity, and that thing's also attached to a piezo transducer, just like the transducer in an AOM. And we'll be seeing kind of the state-of-the-art technology, including the kind of nanoscale optomechanical cavity attached to a piezo, kind of talking to a superconducting qubit. And with that, I'd like to end my introduction here and introduce today's speaker. Right, so it's a great honor to introduce Professor Alp Sipahigil, who just joined Berkeley this year as the Chang Hui Faculty Fellow and an assistant professor of electrical engineering and computer sciences. He also has joint appointments as a faculty scientist at the Lawrence Berkeley Lab, as well as the Department of Physics. His research is in the fields of solid-state quantum technologies, focusing on hybrid quantum devices, ranging from superconducting qubits to nanomechanics, to nanophotonics, and atom-like defects in solids. Before coming to Berkeley, he was an IQIM postdoc at Caltech, where he conducted the transduction work we'll be hearing about today in a group of Oscar Painter. And he also received his PhD in physics from Harvard, where he worked with Michel Lukin on quantum optics of color centers in diamond. He received his bachelor's degrees in physics and electrical engineering from Boğaziçi University in Istanbul. And without further ado, Alp, please take it away.
All right. Thanks so much for the very nice tutorial, Paul, and the very nice introduction. Can everyone see my screen?
Yes.
Yes. Okay, great. All right. Well, and also thank you for introducing me as well. Like Poe said, I'm a new faculty here, just joined this year. And I'll be kind of talking about the building optical interconnect. So just like Poe said, what we want to do is basically make an AOM, an acousto-optic modulator, except we want this acousto-optic modulator to be compatible with extremely low power operations. So what we want to do is to make a transducer that can be so efficient such that if you drive it with a single microwave photon, you can create an optical photon. And the motivation for this work is like Poe said, is to be able to create links, long distance links, and entanglement between superconducting quantum processors using optical photons. Okay, so I don't really need to motivate quantum science and technology to this audience. So mainly the reason we care about these types of questions is because, smart people have told us that if you can control many body states and engineer desired superposition and entangled states, you can do useful things in computation, communication, and sensing. Quantum computing is one of our center's, main focus areas, but there's also other applications too. For instance, quantum communication is one. In quantum communication, the main idea is that when you make a measurement on qubits or quantum mechanical objects, that changes the state of the system. So this property of quantum measurement allows you to realize physically secure communication protocols. And in addition to that, there's also applications of these squeeze and entangled states to reduce noise in quantum measurements. And this is probably actually one of the areas where we're already starting to see kind of the near-term applications of these technologies. Okay, so these ideas have been around. Okay. Right, Dan has pointed out that we're going from AMO to AOM physics, which is correct. So these ideas have been around for a few decades already. And in the last 10, 15 years, the new challenge or the new focus has really transitioned to building up quantum machines that can do these things. And that's one of our center's focus areas here. So the key ingredients for realizing this is the following. So first of all, we need to find a good qubit. What is a qubit? It's a two-level system that you can initialize and control and read out with high fidelity. In order for us to realize a good qubit, we want them to have long coherence times. Physically, what this means is that it requires us to engineer systems, two-level systems that are only weakly interacting with their environment. Okay, so we want systems that are weakly coupled to their environment. But the second requirement is that we also want to be able to create strong interactions between different qubits. That way we can do things like 2-qubit gates and so on. So these two requirements are somewhat contradictory, and it's one of the central challenges for scaling up quantum computers. We want systems that are very well isolated and only interact when we want them to. We just don't want them to interact when they're sitting in some idle state. Okay, so what I want to do next is to give you a flavor of the device landscape in terms of what approaches people are taking for developing solid state architectures. So one of the leading platforms for quantum computing in the solid state is with superconducting qubits. So there's several companies developing these types of systems. I guess today, Amazon, announced their new center at Caltech as well. So Amazon AWS has joined the team here as well. So superconducting qubits, one of their main advantages is that these are, photolithographically defined circuits, and you can realize fast logic gates in these systems. So typical logic gate times, single qubit and 2-qubit gate times are in the range of 10 to 100 nanoseconds. So this is great. So they can interact very strongly. But for the same reasons, because they're strongly interacting systems, they typically display short coherence times in the 100 microsecond range. So in contrast, there are other systems which display extremely long coherence times, like nuclear and electron spins in solids. So these can have coherence from 1 second to even minute, especially for nuclear spins. So these are great qubits and great memories, but they only weakly interact with each other because these are magnetic dipole interactions, and the long-range interactions are rather weak. And then finally, the last solid-state platform I want to highlight is photonics. So here, the advantage is that we love optical photons because you can transmit them over long distances with low loss, but optical photons don't interact with each other. So what I want to highlight is is the idea that we have several platforms, but there's not a single one which can simultaneously achieve long coherence times and strong interactions in the solid state. So one of the things that I've been interested in both in my PhD postdoc, and this is something we're pursuing here at Berkeley as well, is the idea of building hybrid quantum devices, where the motivation is the following. I've just told you that superconducting qubits are great for doing fast logic operations, So the idea we're after is to use different physical platforms which are good at different tasks. For instance, we could use superconducting qubits as our processors. We could maybe use these nuclear and electron spins as our memory modules because they can store quantum information for a long time, and then use optical photons for any communication task. This is kind of like the early days of computing where, people were looking at different platforms, and similar to, how we build our computers as well. We have a processor node, we have a memory node, we have a communication node. So in the quantum domain, so when we're dealing with qubits and quantum level signals, one of the open questions, if you want to implement such a hybrid architecture, is how you actually convert quantum mechanical states between these different physical platforms. For instance, if I had a qubit from a superconducting qubit from a superconducting circuit, how could I transfer that to a spin qubit or to an optical photon and vice versa? So this is an area where there's growing interest, and it's sometimes called quantum interconnect research. The idea is how do you build these modules and how do you connect them with each other? So my PhD work at Harvard focused on looking at part of this puzzle, on building interfaces between memories and optical photons. So I kind of want to spend a few minutes describing an approach for doing that. And in the solid state, one of the leading platforms for doing this is color centers in diamond. I want to highlight a few properties of these color centers, and I kind of provide some numbers for the AMO physicists here. So these color centers are defects in solids. They consist of some combination of external impurities and lattice intrinsic defects. And essentially, you have multiple different types of impurities, and they can form clusters. And what this means is that you end up with systems that have molecule-like properties. So you have electronic spin states and optical transitions that display molecule-like properties. So what we've shown is that especially the silicon vacancy color center combines a number of desirable properties for building optically interfaced quantum memories. So the electron spin associated with this defect has a long coherence time of about 10 milliseconds. And if you couple that to a nuclear spin, you can achieve even longer coherence times. So that's fairly common for spin qubits in solids. So spin qubits in solids typically have long coherence times. What's really special about this defect is that it also displays very coherent narrow optical transitions. So if you have an optical transition, there's a theoretical limit to the line width of that, which is set by the excited state lifetime. And that's usually satisfied in atomic physics. So if you have an excited state with some lifetime, the inverse lifetime determines the line width. This is not necessarily always the case with solid state emitters because there's a lot of noise in the environment and so on. But what we found here was that if you choose systems, if you work with systems that are centrosymmetric, you can achieve first order insensitivity to external electric fields. So basically, if you have an inversion symmetric system, you don't have a linear DC Stark shift effect. So what this means is that you can achieve very narrow line widths at the transform limit. So this is great. It means that we can have very coherent narrowband transitions in the solid state. And one of the advantages of being in a solid state is that you can engineer photonics and devices around it rather easily. So here I'm showing you some SEM image of photonic devices we developed at Harvard, where we integrate single color centers into photonic crystal cavities, and we could reach regimes where we could achieve strong coupling between single optical photons and single electron spins. So with these images here, what I want to kind of highlight is that we could reach a regime where we have an optical cavity, and by changing the spin state of the electron inside, we could modulate the transmission of this photonic device. And for the experts, for the cavity QED experts in the audience, these experiments have reached a fairly high cooperativity regime in optical cavity QED. To my knowledge, this is one of the highest numbers that has been observed. So these interactions are really very coherent, even if you take all the dissipation mechanisms into account. So what does this enable us? What are the interesting physics with these platforms? So first of all, it allows you to push nonlinear optics to fundamental limits. You can realize photonic devices where you have quantum nonlinear response. What this means is that if you send 1 versus 2 photons, the system behaves differently. You can use spin photon interactions to realize photon-mediated long-range interactions. And finally, they have applications in building quantum communication networks, in building quantum repeaters. Okay, so that's past work. I kind of want to highlight some of the activities we're ramping up in my group. So everything I told you about was, photonic devices fabricated in diamond, and that's quite challenging. I mean, we're at the Challenge Institute for Quantum Computing, but I was afraid to take on that challenge here. It was maybe a little too difficult for me. So what we're looking into now in my group is to transfer, what we've learned into developing a new platform in silicon. So we're ramping up a few efforts. What people have shown in the last year is that there are now color centers in silicon that are single photon sources emitting at telecom wavelengths. So in this plot, you can see emission spectrum of a few different color centers that people have reported last year. So we have a new effort in terms of discovering and performing spectroscopy of these new color center qubits in silicon. So this is this is a collaboration with Dartmouth and LBNL. And then together with Boubacar here at EECS, we're working on device integration of these color centers. And then finally, we're also planning for a quantum network testbed. This will be a collaboration with Hartmut Hefner's group, and we're gonna kind of work on doing things like quantum interference between ion trap photons and color center photons. So I guess stay tuned to hear some of these advances, developments. And also I want to thank Paul for doing a great job with the tutorial. He's the one working on this project. All right, so that was kind of a quick advertisement on some of the things we're doing. But in today's talk, I'm going to talk about how we make an interconnect between superconducting quantum processors and optical photons. So the kind of, I guess, the midterm goal for these experiments is to build an optical interface such that we can create entanglement between different quantum processors operating inside different dilution fridges. Okay, so here's the outline of my talk. I'm going to first give an introduction to how we can manipulate quantum information with superconducting qubits. And then I'll go into the nuts and bolts of how we build a quantum transducer from microwave to optics using nanomechanical resonators. Okay, so at this CIQC colloquium series, we've already heard really nice talks, a really nice colloquium on superconducting qubits, but I'll kind of give a quick introduction here for those who I guess haven't had a chance to attend those. So superconducting circuits are electrical circuits made from superconducting elements. The simplest example is an LC oscillator. So the LC oscillator, if you write down its Hamiltonian, it consists of the magnetic energy stored in the inductor and then the electric energy stored in the capacitor. And this looks precisely like the Hamiltonian of a harmonic oscillator. So we know what the solutions to the quantum harmonic oscillator is. We have different eigenstates separated evenly in energy. And in this case, the separation energy between different eigenstates is omega naught, h bar omega naught. And the frequency here is given by the resonance frequency of the electrical circuit. Okay, so this is just a good old LC circuit. How can we make it quantum mechanical? Well, we have to do a few things. First of all, we want to initialize the system in a pure quantum mechanical state. To do that, we need to get rid of all the thermal excitation. So we need to go to KTs, which are much smaller than h bar omega. What this means in practice is that we need to operate much below 300 millikelvin, because the typical microwave frequencies where you can get, test equipment in a relatively convenient way is around 5 gigahertz. That's roughly the frequency we'll operate at. And that puts a limit on the temperature. So that's why we have to work with dilution refrigerators in these types of experiments. But this by itself is not a qubit. So we have many quantum states here and infinitely many ladder of states. So this by itself is not sufficient to realize a two-level system in a qubit. So we need something to modify this harmonic potential, and that key component which allows us to engineer qubits out of microwave circuits is the Joseon Junction. So the Joseon Junction is an element that consists of two superconducting islands separated by an insulating barrier. And for our purposes, this behaves as an extremely nonlinear inductor. So instead of this phi square potential, now we have an anharmonic potential. And because of the anharmonicity of this potential, now the different states in the system are going to be separated by different frequencies. Okay, so if you choose your excitation frequencies to be resonant with 0 to 1 transition, the 1 to 2 transition is going to be off resonant. So you can constrain the dynamics to a 2-level system manifold. Okay, so that's the recipe for theoretically building a superconducting qubit, and this is what they look like in practice. So here I'm showing you an SEM image of a superconducting qubit. The orange shaded area, highlighted area, is a superconducting island that's capacitively coupled to the ground plane. And in addition to this capacitive coupling, we also fabricate Joseon junctions by overlapping 2 nanowires of aluminum with an insulating barrier made out of aluminum oxide. So that component, this Joseon junction, is what gives us the nonlinear inductance needed to make the qubit. So one thing you can quickly notice is that these circuits, these qubits, they're macroscopic. The typical dimensions here are in the range of 100 microns to 1 millimeter. So you could see them by your eyes, yet they maintain quantum coherence. And a nice aspect of, as a consequence of their large size, it's actually really easy to engineer qubit-qubit interactions. So if you want to create, for instance, dipole interactions, the physical scales involved here are so large that you can just lithographically define an arbitrary shape for your circuit to engineer the capacitance matrix and the coupling matrix between different qubits. So by laying out qubits in different geometries, you can engineer different coupling coefficients in an array of superconducting qubits. So that allows you to realize qubit-qubit interactions. But you can also couple the qubits to linear oscillators. So this is how we do cavity QED. So if you couple them to linear circuits, then you can use the cavity modes to mediate interactions or to read out the state of the qubits. So these 2 key ingredients, qubit-qubit interactions and qubit-photon interactions, are the building blocks that people are using for quantum computing with superconducting circuits. So I want to kind of give a feel for where the field is at right now. I guess now already a couple of years ago, the Google team was able to show what they call quantum supremacy in a 2D array of superconducting qubits that had 53 qubits. And in this array of qubits, so here I'm showing you a schematic of the architecture they had. They have this 2D grid where each of the cross-shaped structures corresponds to a single superconducting qubit. So you have nearest neighbor interactions. They were able to reach high fidelity gates between these qubits and show quantum supremacy. But we're far from done in terms of building a useful quantum computer. There's several challenges. These qubits are large. They're, as I've shown you, about 100 micrometers in size. And if you want to do something useful, I think conservative estimates put the need in terms of the number of qubits to about a few million. So if you want to have few million qubits, these large qubits are a problem. So we need to find things that are smaller and still work well. Secondly, they have short coherence times. So the lifetime of these qubits is limited to around 100 microseconds. And then finally, we don't have a good way of sending information in and out of these dilution refrigerators. So we can't network these quantum processors with each other. So on the right, I pulled an image from one of Google's setups just to give you a sense of the complexity of these experiments. I think I'm imagining everyone in this institute who's listening to this talk has seen, tens of images of different dilution refrigerators. It's, I guess, the public thinks, a dilution refrigerator is a quantum computer. Well, it's everything around the quantum computer is most of it is the dilution fridge and the RF cables, but the actual chip itself is just centimeter by centimeter. So what you're seeing here is a zoo of cables, coaxial cables at room temperature and cryogenics, just to control 50 qubits. So we have also, as Paul was mentioning, it's another scalability challenge in terms of how to scalably control these qubits and how to transmit quantum information in and out of these circuits. And one solution for doing that is going to optics, because at room temperature, there's thermal noise at microwave frequencies, whereas in the optical domain, the thermal noise is effectively 0. So I'm gonna discuss 2 ideas and a set of results in 2 directions. I'll show how nanomechanical systems might offer a solution by realizing compact qubits for superconducting circuits. And then I'll show our results on optical photon generation for quantum communication. Okay, so here's the challenge that Paul has very nicely outlined. We want to convert a single optical photon from a superconducting qubit to a single optical photon. This is essentially a problem in frequency conversion. We want to convert a single photon from 5 gigahertz to 200 terahertz, and we need to engineer some nonlinearity to do this. So the medium we choose as our nonlinearity.
So, Alp, I have a quick question.
Yeah.
So I don't know if you talk about that, but for the superconducting qubits, how are they connected? You explained that it is an LC circuit. So when you connect these qubits, is it just nearest? How far does the interaction go?
Yeah. So if you, but typically, I guess one of the most common ones is capacitive coupling. So literally, there's a, I guess in this architecture here, you see these cross-shaped structures. They have, so that's a floating island of superconductor. It has some capacitance to ground. That's the main C that determines the frequencies. But then there's nearest neighbor interactions, which is capacitive coupling. Of course, there's parasitic terms. So you have some, coupling to to the next nearest neighbor as well. But that's something people usually try to minimize in this architecture, at least. Yeah.
Okay, so it's like nearest neighbor. That's it.
Yeah.
So no, it doesn't go far. It's not. There is no long range interaction, basically.
Yes, in this architecture, no, but you can also realize long range interactions as well. So that's mainly if you're using. So what I discussed so far is this qubit part. If I just bring them together, they couple. But then another thing you can do is you can put 2 qubits in a microwave resonator.
Thank you.
And then that will realize long range interactions. So that's what what people do in the optical domain, usually cavity mediated interactions. So people pursue that as well.
Thank you. Thanks.
All right. All right. Okay, great. So this was the introduction to superconducting qubit platform, and in the rest of my talk, I'm going to focus on how we can use mechanics to convert these microwave photons to the optical domain. So I want to start by introducing the phonon to photon conversion part. So how can we couple mechanical motion with light? And a kind of a toy model for describing the coupling of phonons to optical photons is the following. So here I'm showing an image of a Fabry-Pera resonator. So it's an optical cavity where the back mirror is attached to a mechanical spring. Okay, so this mechanical is going to undergo some displacement and some mechanical oscillations. And as this back mirror moves in position by some delta X, it's going to change the size of the optical cavity. And when the optical cavity length changes, of course, the resonance frequency shifts. Okay, so this results in some parametric coupling between the optical resonator and the mechanical resonator. So the operators A and B here refer to the annihilation and annihilation operators for the optical cavity. So that's the A term, and the mechanical resonator. So B dagger creates a phonon, A dagger creates an optical photon. And we can write this parametric interaction with this red term over here. So if your mechanical mode undergoes some displacement by X hat, that's going to give rise to some change in the cavity length and is going to shift the cavity frequency. And I put that term over here because, if I can add that frequency shift onto the bare cavity resonance, which is omega naught. So this X hat, I've just given a classical description. That's the displacement amplitude for the mechanical oscillator. But like Paul introduced, mechanical modes, they're also bosonic fields. Phonons are bosonic fields. So you can do the same quantization that we do with electromagnetic fields, and you can express this displacement operator as sum of creation and annihilation operators multiplied by some 0-point fluctuation of the mechanical mode. Okay, so this is the parametric interaction Hamiltonian. And I can plug in this B dagger plus B. And for the rest of the talk, I'm going to refer to this interaction process as the optomechanical interaction Hamiltonian. So Paul gave a very nice introduction to nonlinear optics and three-way mixing. So this is essentially a three-way mixing process because each of the terms in the Hamiltonian has 3 operators. Okay, so there's A dagger A, B dagger, and then A dagger A, B. And all of these A's and B's, they come from the electric field and the displacement operators. Okay, and the physical meaning of this term GOM is the amount of frequency shift we have for 0-point fluctuations of the mechanical oscillator. Okay, so how can I start with this Hamiltonian and then do phonon to photon conversion? So again, we're going to use techniques from nonlinear optics. What we're going to do is we're going to inject some classical fields, some classical pump fields. And this is going to cause some average displacement for the optical resonator. So we're going to have some coherent state alpha, and then we can expand for quantum fluctuations around that coherent state and denote that by this delta A hat operator. So if I make this substitution, so I take the mean field alpha and then look at fluctuations around it, I can find the resulting Hamiltonian. And then what I'm going to find is that there's going to be terms where the interaction Hamiltonian involves this A dagger B plus A B dagger type of terms. And this precisely corresponds to the beam splitter Hamiltonian, which annihilates a single photon and creates single optical photons. Okay, and physically what's going on here at classical intuition here is that I send a laser field into this cavity. This mechanical mirror is oscillating at frequency omega m, and this is going to cause frequency modulation on the laser field. And I can choose the detunings to be such that I resonantly enhance the upconversion process. So I annihilate one photon from the pump laser field. I annihilate one phonon, and then I create a photon at the sum frequency. So this is a frequency conversion task where we're going from a single phonon to an optical photon. Okay, but this is kind of the microscopics, but when we take a step back and think about the system level, these B's and A's, they're bosonic operators, and I can just define some effective coupling parameter GOM. So this allows us to do that. So, mathematically, this is now very simple. Quantum transduction is just some coupling between two harmonic oscillators. There's nothing more to it. Okay, so how do we engineer these interactions? So what we want to do is to create strong coupling between phonons and photons. In order to do that, we use a platform developed in Oscar Painter's group more than a decade ago now. So they've shown that you can design these structures. So this is a one-dimensional nanobeam of silicon that's suspended in air. And by patterning holes, by making these holes on this silicon nanobeam, you can modulate the refractive index, and that allows you to realize Bragg mirrors for light. Okay, so these are on the two ends. I have these holes that are engineered to behave as mirrors for light. But what's kind of nice and new and surprising is that the same mirrors, they actually behave as mirrors for phonons as well, because you're modulating the mass density, and it also creates a mirror for acoustic vibrations as well. So in the same structure, you can engineer modes, photonic modes at telecom wavelengths. So this is the electric field mode profile for this photonic crystal cavity. And the same structure also localizes mechanical resonances at the 5 gigahertz band. So one thing that's kind of a really nice coincidence of nature is that these two modes, these two waves, they both have the same wavelength of around 1 micrometer, but their frequency is separated by this many orders of magnitude. And the ratio of these two is really determined by the ratio of the speed of light and speed of sound in the materials. But for us, this is a really nice coincidence because 5 gigahertz is where microwave circuits operate, and you naturally have phase matching with telecom wavelength photons. And in terms of the physical strength of the interactions, about a femtometer of motion of this mechanical mode, this is really small displacement, gives rise to a very large frequency shift on the optical resonator, about the megahertz. Okay, and this strong interaction is there because we've co-localized these two modes together. So the electric field energy and the strain field, the elastic energy, they're co-localized, so they strongly interact with each other. Okay, so I'll move on to discussing some of the interesting properties of these mechanical modes for the next few minutes, but I could take questions if anyone has some on this cavity of the mechanics part. No? All right, moving forward. So before I move on to the transduction experiment, I want to highlight some of the results from Caltech on some of the really interesting properties of these mechanical oscillators. So I've
So,
shown you that these.
maybe I have a question regarding so the factor GOM that you explain as the 0-point fluctuation. So I'm not sure I understand exactly what that is.
Yeah, so the mechanical oscillator is a quantum harmonic oscillator. Just like the LC circuit, you can think of it as a quantum harmonic oscillator. And if you cool it down to 0 temperature, the wave function of the harmonic oscillator still has some uncertainty in it, right? Even the ground state has a wave function that has finite uncertainty just because of the uncertainty principle. So that determines what we call the 0-point fluctuation. So even if you were at 0 temperature, if you measure,
does that result in a kind of effective shift of your resonance frequency? Is that the way to think about it?
Yeah, so that 0-point fluctuation gives you the scale of the amplitude you have for a single phonon. So that's the 0-point part. But if you had one phonon, it would have a displacement of that scale. This GOM is just a definition. So it's just the multiplication of this 0-point fluctuation times this coefficient, which is some frequency shift per unit displacement.
Okay, I see.
Yeah. So what we're going to do is we're going to parametrically enhance this interaction. So the effective coupling rate is determined by this GOM times the average, I guess the absolute value of alpha, which is square root of the number of optical photons you have in the cavity. So this basically, GOM is kind of like the fundamental interaction rate, and then it's just a way of specifying what the coupling is at the single phonon level.
Thank you.
Okay, so yeah, before I want to move on, I want to kind of discuss some of the interesting properties of these mechanical oscillators. So if you have a mechanical oscillator, we use that, in our electrical circuits, we make, crystal controlled ovens, quartz oscillators. They're good frequency references because you can make a good oscillator out of mechanical systems. But something really interesting happens when you cool down to really, really low temperatures. So a lot of the mechanisms that limit the quality factors of mechanical resonators get suppressed at low temperature. So in this experiment, we use the optomechanical interaction to probe the mechanical mode that I've shown you, this 5 gigahertz vibrational mode, using the optomechanical interaction. And I'm not going to go into the details of this experiment, but what I want to highlight is that if you measure the quality factor of these mechanical modes at ultra low temperatures at 10 millikelvin, they have an energy relaxation time of about 1 second. So these are 5 gigahertz oscillators. And if you calculate the quality factor for these oscillators, it's about 40 billion. So it's an extremely long-lived oscillator. And I think this is going to be very interesting moving forward as a potential platform for realizing long-lived memories at microwave frequencies. And the reason for that is superconducting qubits, they're large in size, and they're about a millimeter in size, and their lifetime, these are also 5 gigahertz microwave oscillators. Their lifetime is around 100 microseconds. Whereas with these nanomechanical resonators, their lifetime is about 1 second. So several orders of magnitude larger, and they're a lot smaller, 1 micrometer in size. Of course, a mechanical oscillator is not a qubit, right? It's a linear oscillator, but there's been, really nice developments, especially at Yale, in terms of doing quantum computing with bosonic systems. And I think this could be for instance, we had a really nice talk by Michel Degore in this colloquium series. So I think it's very interesting to see if these mechanical modes can be used for realizing quantum computers based on bosonic quantum information. Okay, so in the remaining 20 minutes, I'm going to discuss how we put all of these together, how we put all these things together, put a qubit and this optomechanical transducers to convert a single photon from microwave to the optical domain. Okay, so I've shown you how we do phonon to photon conversion. It's this optomechanical interaction based on this GOM, optomechanical coupling. And what we're missing so far, and something I haven't talked about so far, is the coupling between a superconducting qubit and this optomechanical resonator and the mechanical degree of freedom associated with this optomechanical resonator. So in order to do that, we can use piezoelectric response of materials. But silicon is a centrosymmetric crystal, and it does not have any piezoelectricity. So we need to engineer something beyond that. So we had to develop a new approach. So here's the approach we're going to take. Here's the cartoon picture. We again start with the same cavity optomechanics setup. We have a Fabry-Perot resonator where the back mirror is free to oscillate. But now what we're going to do is we're going to add some piezoelectric material on this mechanical oscillator. So now as this back mirror undergoes some displacement, it's going to apply some stress on the piezoelectric material. And because of the piezoelectric interaction, that stress or the strain field is going to result in some induced charge. Okay, so we can translate mechanical motion to induced charge. And then after that, we can simply wire up this piezoelectric transducer to our superconducting qubit. So this is the recipe for how to make a microwave or superconducting qubit to optical photon transducer. So it looks, if we can realize this, we can realize the following interaction Hamiltonian. So this part on the right, this GOM, that's the optomechanical part. It shows the coupling between the optical mode A and the mechanical mode B, that's phonon-photon coupling. And this piezoelectric, so that's between two bosonic modes, A and B are bosonic modes. And then this GEM term here, that's the electromechanical interaction, is going to give rise to coupling between the qubit, sigma operators, and the mechanical mode given by the B operators. Okay, so that's what we want to realize. And if we can do this, obviously we can go from qubit to mechanics and to optics. But this requires us to integrate superconducting qubits, piezoelectric transducers, and optomechanical crystals in a single platform. And that's what we developed at Caltech. We spent about a year in terms of developing a material platform for doing this. And in the end, we ended up with the following approach. So we developed this device platform that builds on silicon on insulators. So we make our mechanical and optical devices on the silicon layer. And then we use a thin film of aluminum nitride, which is a piezoelectric material for the qubit to mechanics transduction. Okay, and after many layers of lithography, we can make devices that contain piezoelectric transducers, qubits, and optomechanical resonators. And I'm jumping a lot of design steps here, but the central piece of our design is the following. So we've engineered a mechanical mode that does two things at the same time. Okay, so this this is a mechanical mode, and the animation you're seeing is showing the displacement profile for this mechanical oscillator engineered at 5 gigahertz. So we designed this mode to do two things at the same time. The right part of this mode is localized at the photonic crystal cavity. So the part that's going red, that's the part of the phonon which causes frequency modulations on the optical resonator. So this long section here that's our photonic crystal cavity. Okay, and on the left, what we did was we added aluminum nitride such that these displacements also result in some induced charge on electrodes. And then we wired up these electrodes to our superconducting qubit. So as this object undergoes some mechanical motion, it results in induced charge and coupling to the superconducting qubit, but it also modulates the cavity frequency. So you have mechanics to optics coupling at the same time. All right, so this is what the devices look like. So we use standard lithography techniques to make this qubit to optics transducer. This is a centimeter by centimeter chip. So this is a multi-physics problem. So we have microwave waveguides that deliver control and readout pulses for superconducting qubits. And the real science, I guess our science chamber is here. This area is where we have our qubit, our nanomechanical resonator and optics. And then on the right side, we etched away some of the material to be able to bring in optical fiber and then couple the optical light that comes out. This is an optical microscope image that shows the microwave components. So we have the superconducting qubit, a qubit readout resonator. I'm not going to go into that here. And then we have a microwave drive, a microwave coplanar waveguide to drive and read out the state of the qubit. So these components here, they're all fairly standard. This is cavity QED with superconducting circuits. What's new here is that we've added a silicon photonic waveguide that allows us to couple light in and out from an optical fiber. And so we bring combining silicon photonics with superconducting circuits, and the transduction happens in this tiny area over here. This is kind of a nice illustration of the wavelength separation between microwave and optics. So this is our transducer area. We bring electrodes from our superconducting qubit, and this is where we have our piezoelectric transducer and the optomechanical cavity that results in this qubit to optical photon transduction. So basically in this picture, the really new thing here is this tiny piece over here. This is the 10 micron by 10 micron area where the new stuff happens. Okay. And here's an SEM image of that device. This is on the left, we have the aluminum nitride on a silicon membrane that's for transduction from microwave to mechanics. And then we have the silicon optomechanical crystal that does phonon to photon transduction. Okay, so the setup looks like the following. We want to do experiments with superconducting qubits, so it has to be done at very low temperature. So we cool these devices down to around 15 millikelvin. We mount this quantum transducer chip on some PCB. And then we have an optical fiber that we can position at low temperatures using cryogenic piezo positioners. And then we have coaxial cables for exciting and reading out the superconducting qubit. So this goes into the low temperature stage of a dilution refrigerator. We have fibers and microwave cables going down to this chip. And the first thing we wanted to do was to verify that our qubit is alive. So our qubit, we've developed a fairly complex fabrication process. So we wanted to see if our superconducting qubit is behaving as it should, and it indeed did. So here in this experiment, we apply a coherent resonant pulse with the superconducting qubit, and we drive Rabi oscillations. So it's actually a pretty crappy qubit. It has a very short lifetime, but for our purposes, we're going to use this as our single microwave photon source. So we can control it well enough to inject single microwave photons into our transducer. So we can initialize and control and read out the superconducting qubit. All right, so we have our qubit, and how do we go from, now I'm going to take you through step by step, going from the superconducting qubit to mechanics and to optics. So we start with the James-Cummings Hamiltonian qubit coupled to a mechanical oscillator, and this is the spectrum that we're working with. E and G denote the excite and the ground states of the qubit. 0 and 1 give the occupancy of the mechanical oscillator. So we start in the ground state. We apply a pi pulse on the qubit, and then we dynamically tune the qubit frequency. So you can do this by AC Stark shift. That's the approach that we took. So you can apply an off-resonant pulse to dynamically tune the qubit frequency. And then after we excite the qubit, we bring it on resonance with the single phonon state. And these two systems are coupled with some interaction rate, GEM, and they're gonna undergo some oscillation back and forth. So we excite the qubit, and once we let these two systems interact, we observe coherent population oscillations between the superconducting qubit and the nanomechanics. And if we stop the interaction at half the cycle, we can convert the qubit population to a single phonon state. So after we run this sequence, it's a pulsed sequence, we can excite the qubit and transfer that excitation to a single phonon. Okay, so we have converted the qubit to a single phonon. The next step is to do this frequency conversion task. So we can apply this laser pulse to do up conversion of the mechanical excitation of the phonon to the optical photon. So, obviously I'm kind of skipping a lot of technical details here. I'd be happy to discuss these later, but one of the challenges is that we're standing in a classical field, a strong pump field, and we're trying to detect single optical photons that are generated at a 5 gigahertz offset. So this requires us to implement optical filters that can do, carrier suppression by 100 dB. So that was actually one of the challenging parts of this experiment, but we implemented all of those. And here I'm going to show you the results of our experiment, where we measure the transduced optical photons for 2 different initial states. So in one version of the experiment, we leave the superconducting qubit in the ground state. We run this transduction sequence, and that's our control experiment. And then we do the same when the qubit is in the excited state. So when we do that, we indeed find that we get about 3 times more photons if the superconducting qubit was in the excited state. So that was the first observation of optical photon transduction from a superconducting qubit. We got really excited. And then once, this excitement wears out, you start noticing, wait, but if the qubit is in the ground state, I'm still detecting photons. So let's go into that. And also another thing you notice is that this detection probability is quite small. So in these first generation of these experiments, we had transduction efficiencies of about, well, not transduction efficiency, but total system efficiency of about 10⁻⁵. And we're injecting noise photons with a probability of 0.4. But we wanted to go beyond this just excitement and ground state. So in this experiment, what we did was we drove Rabi oscillations of the superconducting qubit, and then instead of using traditional readout techniques, we read out the state of the superconducting qubit by transducing to optical photons. So I mean, this measurement is limited by statistical noise with shot noise because our efficiency is really low. So in this first generation devices, getting this curve took like 2 weeks or so. But it was kind of a cool demonstration. So here I'm going to highlight, some of the properties, some of the numbers and the limitations. Our total detection efficiency from the qubit to the photon detector was around 10⁻⁵. Part of this is intrinsic to the device. So the phonon-photon conversion efficiency is actually the weak part. So that's actually the hardest part of this setup, this platform. And other than that, we also had these insertion losses associated with our filter cavity. So this last 10 to the 2 is something that's really easy to engineer. If you buy nice cavities from, I don't know, SLS or some other place, you can bring this close to unity. But this intrinsic part is a problem. So the device at the chip level, it was showing some inefficiency. And I want to explain that a little bit in the spirit of these colloquium series, discussing challenges and opportunities. So what limits this phonon to photon conversion efficiency is an annoying technical problem, which has to do with laser-induced heating of the mechanical motion. So this optomechanical interaction is parametric in terms of the pump power. So in principle, I should be able to just increase the pump power and increase this optomechanical coupling strength. But you quickly realize that that's a problem because if you increase laser power, that's going to induce some heating of the system, and we're dealing with very low temperature systems. So there's a trade-off here in terms of your efficiency and the thermal noise you build up. And we found that in these one-dimensional structures, this was the limiting factor. So if this thermalization and heating problem can be addressed, then these transducers, there's no reason for them to not approach unity. So several groups are kind of developing new approaches. For instance, Caltech is looking at a two-dimensional design that get better at thermal dissipation, and Tobias Kippenberg's group at Lausanne, they're also looking at other approaches where they include helium-3 exchange gas. But there's also materials science problems, so you can kind of get to the core of the problem and ask, why is there heating in the first place? What's absorbing and so on. But with these improvements, I think it's fair to say that in the next few-year timescale, we'll probably see these systems reaching higher efficiencies and fidelities in the with efficiencies in the 1 to 10% range.
So, another question. So, if you make a 2D design, wouldn't that make the co-localization of the phononic and photonic modes more difficult?
It still works. Yeah, there are designs that co-localize both still. Yeah, it works. So it's done. It's already demonstrated. Okay, so if we can do this, then we can start thinking about measurement-based remote entanglement generation between superconducting circuits. Okay, so that was actually all I wanted to present in terms of that work. And here I'm gonna advertise another, kind of open up another topic for discussions for the following discussion sessions. And I also want to kind of present some of the things we're thinking about in terms of other ways acoustic engineering can advance superconducting quantum computers. So what I've shown you is that we have developed these tools. We now know how to engineer these acoustic modes. Just like you can do photonic design, work with photonic crystals, we can now develop phononic crystals, make phononic crystal resonators, etc. So a lot of the concepts that are developed in the electromagnetics setting, things like Purcell enhancements or optical cavity QED, you can think about what those tools would bring in to advancing quantum circuits. And one of the things we're thinking about in my group is asking this question. So, and the question of, what is the role of phonons in causing dissipation in quantum circuits? And can we use these techniques that I talked about today, these acoustic structures, to improve superconducting qubit performance? So it turns out that there are several mechanisms with which superconducting circuits can dissipate energy by phonon emission. So if you have an LC oscillator or a superconducting qubit, this is kind of like a simple capacitor. In these materials, you can have piezoelectricity due to symmetry breaking, or you can also have effective piezoelectricity due to defects in the solid. And what this means is that your circuit is going to radiate phonons into the bulk of the crystal. So one of the things we're looking at with this team is doing the engineering, phononic engineering around these quantum circuits to improve their properties. So we have some kind of first results. These are simulations done by Eric, which show that this phonon limited quality factor is a very serious effect when you're designing electrical circuits. And by modifying the acoustic environment around, you can dramatically modify the quality factors of these electrical circuits. Okay, so I'd be happy to take questions on that in the discussion sections for those interested. So just to wrap up here, I've shown you that these nanomechanical resonators, they're interesting for several reasons. They have extremely long lifetime, so we might be able to use them as compact quantum memories for superconducting circuits. And I've shown you the first demonstration of optical photon generation from a superconducting qubit. This is essentially a first step towards realizing a vision of having multiple nodes of different quantum computers connected by fiber optical links. And I think I've shown you kind of pieces of this puzzle that we might be able to realize one day, where we can use these superconducting circuits as our processors, and we can develop these quantum transducer modules to convert quantum signals between microwave and optical domains. And I've also kind of shown you some results which suggest that these nanomechanical resonators could be used as memory elements as well. Okay, I also want to acknowledge the Caltech team. So this work was done in close collaboration with myself, Mohammed and Mahmoud in Oscar Painter's group. With that, I'll thank you and be happy to take questions.
Yeah, thank you, Al, for the exciting talk. And the talk is now open for questions. So you'll have about 20 minutes to discuss with the community. Yeah. Maybe I can come back to my question. So regarding these 2D systems to promote heat dissipation, as you explained. So you said that this was done. So is the optical resonator a defect, or is it an extended mode?
It's a defect. It's wavelength scale.
Okay, I see. Yeah, thank you.
Yeah, that's one thing I can comment here on these optomechanical interactions. So and how they deviate from traditional. Let's see where the picture is. Okay, here. So yeah, it's similar in terms of the mode size. The 2D version is similar. You can achieve similar type of confinement in 2D. And one of the things I want to comment is that in acousto-optic modulators or nonlinear medium, you think about energy matching, right? But also phase matching as well. These nonlinear processes, they need to constructively add up over many wavelengths for you to achieve efficient conversion. So one of the things that's different here, there's not really a phase matching criteria because these are wavelength scale objects, right? So they're not kind of repeating over many wavelengths. So that's, I guess, one of the differences in terms of the design. So you don't need to worry about those phase matching criteria in these nanoscale structures. Yeah.
Thank you.
So I have a question. So I'm kind of intrigued by your memory application here, and I'm kind of curious. One of the things that makes classical memories so helpful is that they have, potentially much higher density than the computation portions. So if you were to speculate on what a more dense mechanical memory might look like, and could it be addressable in some way? I'm thinking more like classical, DRAM or RAM or whatever. But
yeah, so I think that's definitely possible. Like just looking at the dimensions here, you see that this qubit on the left is kind of gigantic. It's like a millimeter in size, whereas this nanomechanical resonator is, a few micrometers in size. And you can attach many of these mechanical resonators to a single qubit. So you can have many modes. You can kind of frequency multiplex them. You can design at 4.8, 4.9, 5, 5.1 gigahertz, etc. You can do a frequency division multiplexing, and there are protocols. There's really nice work done by Dave Schuster at Chicago, where they couple a single qubit to many microwave modes. So those are, again, large structures, but we could implement similar things with many acoustic modes. So you can do stuff like, frequency modulate your qubit, create sidebands on your qubit, and make it resonate with, one of the memory locations. So there are techniques like that you can use.
And just as a follow-up a little bit, so in this kind of combined architecture that you're putting forth here with, superconducting qubit, mechanical resonator, optical connection, whatever, how hard is it to have a lot of measurement capability? Because one of the things that's going to be really important moving forward with error correction and all that sort of stuff is being able to have a high kind of bandwidth of measurement in addition to the computation and so on.
Yeah, so the measurement here, the most successful way of doing it is using circuit QED techniques. That's the one that's going to still be the best. So you'll still, even if you want to read out the mechanical oscillator, you would go back to coupling it to the superconducting qubit and then reading out the superconducting qubit. That's the most effective way of doing it. So I think the state-of-the-art readout bandwidth is, I guess the time scale is around 100 nanoseconds. So people who are trying to push that, can do the readout in 100 nanoseconds. Yeah. And yes, those techniques apply here too. So that's the microwave part of the story.
So we have a question.
Sorry, go ahead. In terms of where these optical part fits into scaling up quantum computing, I think the bandwidth of the optical part is a serious limitation. So right now, I think it's more suitable for communication and repeater applications. So I think in terms of doing something like distributed quantum computing, at the moment, it's very far from the bandwidths you would need for that. Again, there could be improvements to increase those bandwidths, but right now it's quite limited.
Can you guys hear from the watch party?
Yes,
okay.
We can.
Charles, thanks. Hi, thanks for the nice talk. I have a quick question about some very optical mechanics focused thing. So and I wrote it in the chat, so I'll just read what I wrote. I asked if there are any tantalizing prospects for pushing your system into the single quantum strong coupling regime, and if you think that reaching that regime is important at all for the future of making these hybrid quantum devices better at functioning as network devices or for some other use that I can't immediately think of.
Yeah, very good question.
Mechanical qubit.
Yeah. So that's a very good question. I think it's really hard, like really, really hard. And we could get there maybe, but it's quite challenging. So we're far from it at the moment. I think what that would enable, as far as I know, you could start using that to realize mechanical nonlinearities, and that would allow you to realize optical nonlinearities at the single photon level. So basically, if you had strong single phonon level coupling, like your GOM is larger than GOM square is larger than kappa and gamma. So if you had high cooperativity at the single phonon limit, then your optical response of your cavity would become quantum nonlinear. So without having any other qubits, you could start generating single photons and stuff like that. So that's one area where it would enable new things. But I think we're far from it at the moment, as far as I know. Yeah.
Thanks.
For the transaction part, this parametric approach is sufficient. For if you just want to do this beam splitter Hamiltonian, you don't have to be in this single phonon strong coupling regime. All right, Paul, I interrupted you twice. Go.
No worries. So I see that Hartmut is raising his hand. So please go ahead, Hartmut. Hartmut? Okay, maybe he doesn't have the question anymore. Maybe I can ask one, actually, kind of following up on the bandwidth comment. So how far away are we from, say, imagining, doing pulse shaping on the optical pulse, using, shaping the optical pulse through the microwave?
I mean, so the output pulse, optical photon that you're generating, it follows the pump pulse shape. This is like, in some ways, this is very similar to Raman scattering. So your output field in this approach, so this is the coherent coupling part between the optical mode and the phonon. So in this experiment, you're actually operating the Purcell regime. So gamma, the optical, or kappa, the optical cavity decay rate, is larger than this GOM. So basically what happens is that you get adiabatic following. So the output single photon pulse shape matches the input pump photon pulse shape. So whatever input photon pulse shape you're sending in, the output single photon pulse shape is going to be determined by that. Like you have in, for instance, cavity enhanced Raman scattering. You can engineer the output single photon pulse shapes, like what Gerhardt-Jampe does, for instance. So you can do the same things here.
Okay, then let's take one from Hartmut then.
Yeah, thanks, Ad, for the great talk. I want to come back to the discussion Kubi kind of started in terms of thinking about the architecture and the usefulness of a quantum memory. And I wonder what is known really about how useful a quantum memory is. And in particular, one concern I have, if you have a quantum memory, you're going to need to do some quantum error correction. And doing quantum error correction on a quantum memory is not really feasible. So, yeah, I mean, I always thought the quantum memory is something really cool to have, important. It adds flexibility, but now thinking a little bit more about it, I actually question whether there's actually a use for quantum memory.
Yeah, so I can comment on that. I think there's two areas. One of them is in communication. In quantum communication, there's absolute timescales that matter. If you're doing gates, right, the only thing is, your decoherence rate versus gate time. That's the primary figure of merit. And, absolute timescale, yes, is faster is better, but, it's maybe secondary. Whereas when you're doing quantum communication, your qubit, error corrected or not, has to have a coherence time that's longer than propagation times in the system. So if you're trying to distribute states, at 1,000-kilometer level, that takes, 10 milliseconds or so. So you need to, this quantum memory kind of narrative, I think, just originates from that part of the literature. And you absolutely need it in that case. In terms of, what does it mean for quantum computing architecture? One thing I can comment on that here is that, I guess, you said you need to do error correction on it, but here we have, I guess the motivation here is that the time scale is just extremely different. So if you had, just passively without error correction, if you had an object that has, let's say, second time scale coherence, yes, it would be better with error correction, but just, physically, as a starting point, it has a lifetime that's longer than what you can get with superconducting qubits.
And actually, I think following that line, if you remember from the compiling talk we had a few weeks ago, if you take a large quantum circuit and operate on it, there are bits that sit around for a while other ones are being computed on. And so being able to shuffle them off to a very long coherence time temporary storage could actually be very helpful. you know, because there are these bits that are effectively idle while a whole bunch of other operations are going on.
The trouble though is I need to do this below the fault tolerance threshold, because, but if I shuffle them there and okay, I need to do at some point some quantum error correction on them. And I need to make sure that within one cycle of getting them there into the memory and retrieving them, I'm not occurring too many errors so that I can't correct for it any longer. This is a little bit my worry here.
Oh, you are talking like 4 orders of magnitude longer coherence time, right?
It's not about the coherence time, it's about the interface.
Sure.
So there is an interface, and those interfaces are difficult. They are not, I mean,
so I agree with that. You would use it, I mean, you don't want to do hundreds of gates on this thing for sure. It's definitely bad. It's one time in, one time out, and there's going to be some error associated with that. And that has to be above error correction threshold. I agree with that.
Yeah, and this is kind of my, like, you need then really an error rate of below 1% or ideally 10 to the minus.
I think that might, I mean, we haven't focused on that here, but I think that's, if not shown, I'm sure will be shown. It's not actually just, it's not that difficult. So Amir Safavi's group has been kind of pushing on that frontier, and they've achieved, you know, qubit phonon cooperativities that are quite large. And yeah, I don't know the latest numbers, but I think that's definitely within reach. And a second thing I want to highlight is with this bosonic error correction, that's another direction. It's not it's different from the main paradigm, I guess, for gate-based approaches, but kind of implementing these bosonic error correction cat qubit codes in these mechanical oscillators, I think another interesting area.
You know, also, if you could entangle sort of the syndrome and then put things in this memory and then, you know, measure the syndrome in a different system, there might be a way to at least suppress errors while the bits are still sitting in the memory. I don't know, I haven't really thought this through, but it might be kind of interesting to consider ways in which you could help the bits be more stable over a longer term.
Alp, you showed a one-dimensional geometry for the connection between light and phonons.
Mm-hmm.
If we departed from that, is there a different construction geometry that would give you certain advantages? You know, I can imagine obviously being, you know, intersecting nodes and some kind of interconnectivity of different optical and phononic modes. You could imagine a setup that has maybe some symmetries and therefore some degeneracies within it.
Yeah, I mean, I think this is an interesting question. This was kind of brute force numerically optimized, I can tell you that. But as a kind of initial seed starting points, there could be better starting points. And I think, you know, it's kind of an interesting optimization problem. Maybe using more novel techniques, you know. Yeah, so people are now creating, you know, photonic structures that are completely counterintuitive. You define a figure of merit and you ask, you know, some complex optimization to produce you a better design. I think there's definitely possibilities for that. Yeah, but if your thinking is like you have two degenerate optical modes that are kind of hybridized as a function of some displacement, one of the challenges is getting degenerate modes, like really degenerate modes with these types of structures is really hard. So that could be challenging.
Is that true for the acoustic modes also?
Getting exact degeneracy, I mean, because these are really high Q modes, right? So you have very sharp lines, and getting them to be exactly degenerate is quite challenging. So I can tell you that, you know, we design, I mean, in terms of design, this is, you know, a very engineerable platform. So you design something for, you know, 5.1 gigahertz, you calculate, you simulate this optomechanical coupling, you know, you simulate to be megahertz. And then what you measure is, you know, typically within 5% of all of these parameters. The frequencies, the optical frequencies are, you know, within 1% or so. the coupling parameters also come out to be, within a few % of what you simulated, but, not exact degeneracy still. That's still difficult.
How do you tune the acoustic system?
You can't. You just can change the, the parameters, the geometry you're designing. In situ tuning of acoustics is really hard. There are some experiments where people bring an AFM tip, they oxidize the surface to change the density. And you can do this in situ. You can optically characterize and bring in an AFM tip and oxidize different locations to tune the mechanics, but kind of not super practical for these types of experiments. So it's done basically once you design it, it's done. It's not a nonlinear system, it's a linear system, so it's hard to tune. You could have, of course, optical, what's the like spring effect to do some kind of frequency shifting that way, but it's not a lot.
Right, then everything's hot, and that's not so great. Right.
Yeah.
I also had a question about this optical heating effect that was affecting your transduction. So do you know if that's heating of the confined phonon, or is it heating of the qubit, or what? Is there some way of separating the effects?
Yeah. So it's the phonon temperature that's limiting. So when you have, and you were sending, a classical laser field, and even if you absorb one photon, that's a very, the h bar omega is very large for the optical photon. So that energy needs to get dissipated somewhere. And this would get absorbed at that cavity. So there's like a hot spot there. So you absorb a photon, and then you create these very high frequency phonons. And then they gradually down convert these hot phonons, these high frequency phonons, gradually down convert to low frequency phonons, and start building up some thermal occupancy for your 5 gigahertz oscillator. So there you start with like optical phonons, and there's kind of 3-way mixing for phonons, frequency coercion, and it gradually starts heating up the mechanical mode. But it all happens in the mechanical domain. So the qubit, there are other things that happen to the qubit, other bad stuff, which I haven't talked about. But this, the part that limits this transduction is mechanical.
And then Alp, there were promises of big like optomechanical crystals. Has that not come about because because of what? Because of the irreproducibility of the different elements? Like
what Florian Marquardt type thinking of? Yeah, so inhomogeneity is a challenge. So if you wanted to, take this building block and make novel metamaterials, acoustic metamaterials, or metamaterials for both, optics and phonons, and engineer an array of these structures, you're limited by the disorder. So I think there's really nice work kind of happening already, but the challenge there is this disorder that you have, like side-to-side disorder in arrays.
Okay, any other questions from the audience? Hartmut, do you have another?
No, sorry, I just forgot to lower my hand.
Okay, if there are no more questions, I think next we have a session.
Lisa B01. Hello, Lisa B01. This is great. Okay.
Any questions from Lisa B01?
Yeah, no, thank you, Al, for the great talk.
All right. Thank you, everyone.
Yeah, thank you. And so all the PI should leave.